Yeah. So welcome back everyone to this first day's afternoon session. Two announcements. First of all, for the next session, there are two talks missing, so please upload them in the Indico website. And apart from that, the final discussion will be skipped because we have to be at like 7:30 at the theater. So we leave exactly.
Okay, perfect.
And yeah, let's welcome Maykoll Reyes, who is from University of Saragossa, and he's going to talk about the effects of Florence invariant violation on extragalactic high-energy neutrino flux.
Okay, thank you very much. My name is Maykoll from University of Zaragoza, and I'm going to talk briefly about the basis of my work with José Manuel Carmona, José Luis Cortés, and Javier Relancio. I'm going to present the basics of a toy model which aims to predict or make some predictions about the effects that will have Lorentz invariance violation in the flux of detected neutrinos. So this first slide are going to overlap a little bit with the other presentations of this morning because we start from the same point, the unification of quantum mechanics and general relativity. In order to make this, we need to change our conception of the space and time. And one natural way to do that is to break the fundamental symmetry of space-time, which is the Lorentz invariance. So, considering Lorentz invariance violation, we know that these effects are supposed to be small at the usual energies, but these effects becomes relevant at higher energies, and also they are accumulative, so they increase with the distance traveled by the particles. Taking this into account, a good place to start looking for new physics, for this kind of new physics of Lift, is the observation of high energy extragalactic astroparticles. Being more specific, we can focus on neutrinos because neutrinos are very good messengers because they almost don't interact with anything during the travel. Also because they could already contain effects of new physics, like for example their masses. And also, of course, because in the last decade, we already have access to observations of these high energy neutrinos, thanks to the observatories like IceCube, the ones who detected the first PeV neutrino. So now, how we approach to LIF, to Lorentz invariance violation? Was at the underlying ideas of Lorentz invariance violation comes from quantum gravity, and they are still unknown. There are many different frameworks, many different ways to approach to Lorentz invariance violation. The most used one, I think, is the standard model extension. But in this simple model, we want to concern only about, we want to deal only with the effects of Lorentz invariance violation in the neutrino sector. We don't want to consider about the effects in other particles. This can be done also using the standard model extension, a non-minimal standard model extension, but also putting a gauge violating term. But in any ways, we are not focusing in the framework because these different frameworks, all of them, leads to a modified dispersion relation. And this is the one we are going to use without bothering, without concerning about the framework they came from. The modified dispersion relation depends on the parameter n, which is the order of the correction, and the Lift parameter that is usually written as the inverse of a energy scale, which is sometimes, most of the time, associated with the Planck mass. If we particularize this dispersion relation to the neutrinos, approximating the neutrinos massless, and we focus in the superluminal case, we obtain a dispersion relation for the neutrinos that makes the neutrino unstable. So now the neutrino can disintegrate through vacuum pair emission and also the neutrino splitting. In the vacuum pair emission, the neutrino is producing a pair electron and positron, and as these particles have a mass, this requires a minimum of energy. So this is a process with a threshold that we call E star. Of course, this threshold depends of the scale of new physics. Otherwise, in the other hand, the neutrino splitting, if we consider the neutrinos massless, as the neutrino splitting consists in one neutrino splitting in three neutrinos, or actually two neutrinos and one antineutrino, if we consider the neutrino massless, there is no threshold for this process. Then, how we compute this toy model? Well, we can start considering a neutrino who travels freely from the emission to the detection, and he is going to lose energy just by the expansion of the universe. But this loss of energy is perfectly defined, is just the redshift. But in the moment this neutrino has enough energy to produce a vacuum per emission, the neutrino will suffer a certain number of disintegrations during the travel, and in which in each disintegration the neutrino will have a probability density for the final energy. So now the energy of the neutrino becomes probabilistic. We don't know the exact energy of the neutrino, so it's difficult to follow the neutrino during the trajectory. We can still define quantities like the mean energy loss at each disintegration. And in this simple model, what we do is to identify the neutrino energy with its mean energy during the travel. In this way, we can follow the neutrino. If we do this, the equation I presented before becomes like a rule for the evolution of the energy of the neutrino at each disintegration. So now, adding this solution to the expansion of the universe, we get a rule for the evolution, a differential equation for the evolution of the energy of the neutrino, considering VPE and expansion, vacuum per emission and expansion. We see that the loss of energy due to vacuum per emission can be written in terms of an energy scale that appears naturally as a combination of the other scales involved in the decay width of the part production, and also the Hubble parameter. If we solve this equation between two generic points, we see that the relation between the energy and two different points of the trajectory change from the classical expression to this new expression. In this new expression, we can identify two very different regimes. If the energy of the neutrino is above the threshold, above the scale of energy, we are in a very strong regime. We don't need the energy to be much larger than the scale of energy, only greater, because, thanks to the very big exponent. If the energy is greater than this scale of energy, we are in the strong regime, and the change in the energy is very, very large. And also the effect is very, very fast for the same reason. And if the energy is below this scale of energy, we are in the negligible regime, in which this guy is almost zero, and we recover the classical equation. So we see that this scale of energy acts like an effective threshold of the disintegration. But we should remember that we also have the real threshold. So which of these are the dominant threshold we are going to measure? Well, is the biggest one, but which one is the biggest one? This will depend on the scale of new physics. So if we plot the quotient of these two scale of energy as a function of the energy scale of new physics, we see that the greater one is the real threshold. So this is the dominant, but this can change for greater enough scale of new physics energy above the Planck scale. Okay, But we are interested mostly in the cases in which the scale of new physics is below the Planck scale. So we can say in that case that the real threshold is always greater than the effective threshold. And let us notice also that if the neutrino is suffering BPE, is because the energy of the neutrino is above the real threshold, and that means that he's also above the effective threshold. So we are always in the strong regime. The effects happen very strong and very fast. Then, if we try to compute the flux for certain energy of detection, once the energy of detection is fixed, we can go back and identify the necessary energy of emission to each point, each location of emission. And we simply then we have to integrate during all the for all the distribution of sources, point-like sources, the contribution of each source, which is the luminosity, which depends on the energy of emission, which can be written in terms of the energy of detection. This is for a classic flux. Now, if we try to do the same in the case of vacuum pair emission, what we get is that for certain location, for certain source, in order to be detected with energy EV, it has to be emitted with energy infinity, with an infinite energy. That means that we cannot have sources that contribute to the flux with of energy EV that are above this critical source, because in that case it would require an energy bigger than infinity, and that's not possible. The implication of this is that the integral, which previously included all the range of possible sources, now is only up to this critical source. And if we increase the value of the detection energy, we are trying to know the flux, the critical source is getting closer and closer and closer. And at a certain point, the critical source would have the same value of the first source we are taking into account, even if the source is at 0. So at this energy, such that the critical source has the same value as the first source we are taking into account, the flux will be 0, identically 0, independently of the distribution of sources or any other thing. So we can say there is a cutoff, independently of the other parameters. And it can be no troublesome, but you have to do numerically in order to solve this equation. You have to do it numerically, but it can be demonstrated that the solution of this equation can be approximated by this expression, which depends on the dominant threshold, the scale of energy of the dominant threshold, which in this case is the real threshold, divided by 1 plus the closest source. Okay? So now, how we add the neutrino splitting? Well, first we have to realize that as we are in the strong regime, the effect is very strong and almost instantaneous. So we can use an instantaneous approximation in which we substitute the emitted neutrinos just in the source by the number of neutrinos and by the effective number of neutrinos at the end of the disintegration shower. Okay, in the case of BPE, is the same number of neutrinos, but the energy is now the threshold energy. As the neutrino splitting has formally the same form in the decay width, and it can also be written in terms of an energy scale, which is an effective threshold for the neutrino splitting, and the dominant one because it's the only one we have in the neutrino splitting, we can do the same, and we can apply also the instantaneous approximation, in which substitute the emitted neutrinos by the number of neutrinos in the end of the shower. Doing this, we can describe the effect in the same way for both, and we can add the effects, and we can add this effect to the effect of the expansion also. If we compute the energy scale of the neutrino splitting, we see that is below all the scale of energies that were characterizing the BPE. So that means that the neutrino splitting is a dominant effect in this case, because if we imagine a particle which is losing energy until they reach the threshold of the BPE, they will continue losing energy until they reach the threshold of the neutrino splitting. So now, as the dominant scale of energy is the effective threshold of the neutrino splitting, now the new location of the cutoff is the scale, the dominant scale, which is the neutrino splitting threshold, effective threshold, divided by 1 plus the closest source. Okay? So now, summarizing what we have done, we know that a superluminal modified dispersion relation predicts a cutoff in the extragalactic neutrino spectrum independently of the shape of the source distribution. This is good because we don't know exactly which is the source of the source distribution of the punctual sources of neutrinos. Then the location of the cutoff depends only in the dominant scale, in the scale of the dominant threshold, and the location of the closest source. Then the dominant threshold that governs the location of the cutoff can be a real threshold, but can be also an effective threshold, depending on the value of the scale of new physics, as we have said before. But fortunately, for a scale of new physics below the or equal to the Planck scale, the hierarchy of the energies are the same. So the location of the cutoff is always governed by the neutrino effective threshold. Finally, we can write the location of the cutoff as a function of the scale of new physics, and vice versa. And this can be done to get some numbers. That is what is maybe what you are missing in the presentation. So now, for example, recently IceCube have discovered a 6.3 PeV neutrino, which is the most energetic detected so far, compatible with the glass-shot resonance. So if there exists a cutoff due to this effect, it has to be at energies greater than this energy. So if we write the scale of new physics as a function of the cutoff energy, we can put a constraint, a bound, in the possible values of the scale of new physics. In this case, for n equal 2, and using a cutoff that has to be at least at this energy, we get that the scale of new physics has to be 0.003 times the Planck mass, the scale of Planck. But we can use this relation the other way around. For example, we can ask where we are supposed to be, are supposed to see a cutoff if the scale of new physics is in fact in the order of the Planck scale. And putting this information for n equal 2 in the expression of the cutoff as a function of the closest source, we are going to consider 0 the closest source, and the scale of new physics equal to the energy of Planck, we get that we are expecting a cutoff near 100 PeV. Okay, and this is very good because future detectors like IceCube Generation 2 aims to be sensible up to exa-electron volt. And that means that the next generation of detectors could be already be sensible to effects of new physics that stem from a scale of new physics around the Planck scale. And that's all. Thank you for your attention.
I don't see any questions.
All clear. Yes, thank you.
The next talk will be by Domenico Frattulillo. And he's going to talk about Planck scale deformed relativistic transformation.
I start? Yeah. Hello, everybody. I am Domenico Frattulillo, and I am a PhD student from the University of Naples. And my talk is about Planck scale deformed relativistic transformations in curved spacetime. And in particular, I will consider de Sitter spacetime example. But let's start with an introduction to DSR theories in flat spacetime. In the last years, many models with modified dispersion relations have been considered, and this is an example where F in principle is a generic function of the energy, the momentum, and the mass of the particle, and L is the deformation scale, that is an inverse momentum invariant scale supposed to be of the order of the inverse of the Planck energy. In the next of the presentation, we will only consider deformations that are linear in the product L times the energy of the particle, because higher order correction will produce effects too small to be measured. Now, if we consider the standard Lorentz transformation, we will not have a relativistic theory because we have deformed the dispersion relation. So in order to construct a theory that is still relativistic, we also have to deform the transformations that connect inertial observers in order to accommodate this new invariant scale. And the name of this theory is DSR theories, where DSR means doubly special relativity. Let's start with the formulation of covariant kinematics in a 1+1 dimensional flat spacetime. And let's introduce the phase space variables xt that are the usually spacetime coordinates, and pi and omega that are the conjugate momenta to x and t defined by the standard commutation relation with the coordinates. We know that Minkowski spacetime is invariant under the standard Poincaré algebra, and these are the commutation relation between the generators. And here P is the standard spatial translation generator, E is the time translation generator, and N is the boost generator. And we have called C the Casimir of the Poincaré algebra that is given by E squared minus pi squared. Now let's talk about the Hamiltonian formulation of a covariant kinematics in this spacetime. We can use H equal to the Casimir minus the mass squared of the particle as Hamiltonian of our system, and H equal to 0 is the on-shell relation. And we can generate in a covariant way equation of motions in terms of an auxiliary parameter lambda in the following way. If we consider the Poisson bracket between the Hamiltonian and a generic function f of the phase space variables, and we set h to 0 in order to take into account the on-shell relation, this is f dot, that is the derivative of f with respect to this parameter lambda that we have introduced. Now we are interested in deformed kinematics in Minkowski spacetime. So let's start from the standard Casimir of the Poincaré algebra and let's deform it at the Planck scale. Here L is the deformation parameter, and as we have said before, we will only consider deformations that are linear in the deformation parameter. And so we have to deform this Casimir with terms that are cubic in the energy, because L is a length scale, and here alpha and beta are two parameters. Now, if we consider the standard Poincaré algebra, this is not a symmetry algebra of this theory, because the boost generator does not commute with this Casimir because we have deformed it. And so, in order to have a relativistic theory, we have to deform also the Poincaré algebra, and we want that C, that is the deformed Casimir, commutes with all the generators of this algebra in order to have a relativistic theory. And here I present a relativistic algebra that is compatible with this Casimir, and here there is a representation of this algebra in terms of the phase space variable that we have introduced before, xt, and the conjugate momenta pi and omega. And also in this deformed situation, P is interpreted as the spatial translation generator, E as the time translation generator, and N as the boost generator. Now, if we use the Hamiltonian formalism that we have introduced before, we can calculate the velocity, for example, of a massless particle, and we have to calculate the Poisson bracket between the Casimir and the spacetime coordinates x and t, and we can obtain the x and the t, that is the velocity of a massless particle, that is equal to 1 minus L times the momentum of the particle. So we will have a velocity that is momentum dependent. Now let's consider the following experiment. We consider a soft and a null photon, with momentum respectively ps and ph, where ps is the soft momentum that is supposed to be much smaller than p hard. These two photons are emitted simultaneously by a source and according to an observer that is local to the source. And we ask with which time delay these two particles arrives to our detector, and we have called capital L the distance between the source and the detector. Now, if we calculate this time delay in the source reference frame, we obtain the following result that is given by the product of the L, that is the distance between the source and the detector, L, that is the deformation scale, and pH, that is the momentum of the R particle. And in this calculation, we have neglected the correction due to Planck scale deformation to the soft photon because its momentum is much smaller than pH. But this is not a physical quantity because it has been calculated in the source reference frame and not in the detector reference frame. So we have to change our reference frame and recalculate the delay in the telescope reference frame. And if we do this, we obtain the following result that is not equal to the previous one. Let's see what's happening. If we are in the source reference frame, we see that the two photons are emitted simultaneously according to an observer that is local to the emission. And the two photons travel at different speed because we have a deformed velocity for the photon that is momentum dependent. And so we obtain the previous result for the time delay that does not depend on alpha and beta. But if we consider the detector reference frame, this is a distant observer from the source. And so we have to act with translation generator on the word lines in order to calculate the time delay in this reference frame. But if we look at the representation of the Poincare deformed algebra, the time translation generator is not trivial, it is deformed at Planck scale. And so when we act with the time translation generator on the word lines, the action of the time translation depends on the momentum that the particle carry. And so the two word lines will be translated differently, and we will have a relative locality effect. That means that the two word lines in this reference frame do not cross in the source origin. And so the expression of the time delay will change, and we will obtain this new result that is different from the previous one. Now, in this example, we have considered two observers that are distant but at relative rest. But because the main sources that are used to test this kind of models are GRBs that are supposed to be not only distant sources, but also highly boosted with respect to us, we can ask what happens to the time delay when the relative speed between source and detector is taken into account. To do this, we have to calculate how coordinates and momenta transform under a finite boost. And we have to consider this kind of differential equation where n is the boost generator and c is the boost parameter. And here a is a generic function of the phase space variables. If we solve this kind of equation, differential equation, we can calculate the time delay in the detector reference frame, and we will obtain this result that again is amplified by the distance from the source between the source and the detector, depends linearly on the momentum of the R particle, but it is exponentially suppressed by the boost factor e to the minus 3c. And let's notice that in this expression, all the physical quantities are calculated in the detector reference frame. That is what we want to do. Okay, this is an example in the flat Minkowski spacetime, but we want also to take into account curvature effect to the time delay. And the simplest way to do this is to consider the Sitter spacetime. That is a maximally symmetric spacetime, and so the calculation is easier. We start from the standard de Sitter algebra, the undeformed one, where h is the Hubble constant, and when we send h to 0, we recover the standard Poincare algebra. And again, we have called E the time translation generator, P the spatial translation generator, and then the boost generator. We will work in conformal time coordinatization, And here x is the spatial coordinate and eta is the conformal time coordinate that is related to the comoving time by the following relation. And again, we can define pi and omega, the canonical moment, the conjugate momenta, that are defined by the canonical commutation relation with the spacetime coordinates x and eta. And we can use these phase space variables that we have introduced to represent in the standard way the de Sitter algebra in the following way, and a Casimir of this algebra is the following one. And as in Minkowski spacetime, we can use the Hamiltonian given by the difference between the Casimir and the mass squared of the particle to describe in a covariant way the evolution of the system with respect to an affine parameter lambda. Now, as in Minkowski spacetime, we want to consider an example of deformed kinematics, and so we will deform the Casimir of the de Sitter algebra at first order in the Planck scale parameter L. And again, the standard de Sitter algebra will be not a symmetry algebra due to the deformations. And so, in order to construct a relativistic theory, we also have to deform the algebra of symmetry. And here there is an algebra deformed that is compatible with this Casimir. And here there is a representation of this algebra in terms of phase space variables. And again, as in the Minkowski spacetime example, we can use the Hamiltonian formalism to calculate the word lengths of particles. And the first thing that we have to do is to calculate the velocity of a massless particle using the commutation relation between the Hamiltonian and the spacetime coordinates. And we can obtain the following result for the velocity of a massless particle that again is momentum dependent. And if we integrate with respect to the conformal time this expression, we obtain the expression of the deformed word line in this curved spacetime. And now we are ready to calculate, to present the result for the time delay when we consider two observers that are distant and boosted. And I have presented the result in the limit e to the minus xi much smaller than 1, because we suppose that the GRB that are the main sources used to test these kind of models are largely boosted. And so e to the minus xi is much smaller than 1. And so this is a good approximation. And so the result that I have found is the following one. And again, as in the Minkowski example, the boost suppress exponentially our time delay. And here Z is the redshift distance of the source. We again have a linear dependence on the momentum of the particle. And if we send h to 0, these terms goes to 0 and only the first one survives, and the result tends to the one that we have found in the Minkowski spacetime. So that's all. Thank you for your attention.
We have time for a couple of questions.
Thank you for the nice talk. Why do you work with conformal time? Is there a technical motivation or physical motivation instead of the common time?
Yes, it's only the calculation are easier because the expression of the Casimir is the same that we have in Minkowski times a conformal factor, and so it's look like Minkowski and the calculation are easier.
Okay, can I have one more? And of course, this is 1+1 dimensions. Did you try to work out the 3+1 dimensional more realistic case?
Not yet. I
Because
haven't
of
considered
technical problems, or is it straightforward, or what do you expect?
I think that it's maybe it's more difficult because we have also rotations, but and yes, I have to consider the commutator between rotations and boosts. There are all other two boosts, and so the deformed algebra will be more difficult, I think. But I don't know if the calculation is straightforward or not.
You haven't tried?
Yes, I have to.
Okay.
Yeah.
Thanks.
You have obtained the expression of the time delay considering just a deformation of the Poincaré algebra in the one particle system. I mean, you didn't need to specify which happens in the multi-particle system, that is the Hopf algebra structure. No? But on the other hand, yesterday, Professor Lickman showed us that the relative effect is obtained when one has a non-trivial composition law. And in fact, this effect depends on which is the composition law. So how is it possible that you obtain an expression for a time law without specifying which is this algebra in the multi-particle state, that is without specifying which is the composition law?
Yes, because I have considered non-interacting particles, and so this is a model for the single particle each.
So this is a different effect. This relative locality effect is completely different to the one we saw in the DSR lesson, because in that case they depend in the composition of the system, the interaction.
Yes, here the relative locality effect is due to the fact that the time translation generator is deformed, and so it has a deformed commutation relation with the coordinates.
No, I understand this effect, but I see that they are different.
But I can. Yes, here there is no composition law.
There is time for one more question.
I just wanted to add to Jose Manuel's comment that this is the limit in which particles don't interact. So it's the same effect, but it's just a limit where you can neglect interactions. Of course, in principle, you can have, as Domenico was saying, this limit. So in principle, you can have other additional effect when you consider interactions, but they should reduce, you expect that they reduce to this limit when you can neglect.
The effect that was discussed in the DSR lesson, all the effect came from the interaction term. If you don't have interaction terms, you don't have convection as we explained.
I think it's a very good point, and actually, I didn't think about it, but my offhand answer would be that in the example that I considered yesterday, it worked because there was kind of a consistency between the translation invariance and the two particles. So to put it differently, there was consistency, which is really guaranteed by the fact that behind all this construction there was a Hopf algebra playing a role, which made all this thing consistent. In this case, actually, I'm not completely sure if it actually there is a Hopf algebra. So if you start considering the same effect from the point of view of interactions, you're going to get the same result. But as it stands, assuming that everything works, we know that there is some Hopf algebra for the zeta. So I think at the end of the day it may work, but.
Thank you. Yeah, there's no more time for other questions. So. And welcome Maria Grazia di Luca, who's going to speak about quantum gravity phenomenology with multi-satellite telescopes.
Can you hear me? Closer. Okay, let's switch now. Okay. Okay, so hello everyone. My name is Maria Grazia di Luca, and I am a PhD student in Naples. So today my talk will be about quantum gravity phenomenology with multi-satellite telescopes, and I will focus on the more conceptual part, not going through any mathematical details, because I'm more interested in presenting the perspective that we are developing and that we think might become relevant for the future generation of satellites. So, as we know, quantum gravity phenomenology aims to account for some effects of the Planck scale physics using a bottom-up approach. And in particular, even though no self-consistent theory of quantum gravity has been proposed so far, some common intuitions arise from different models, and a tentative phenomenological description of such features could lead to testable predictions. So now, the energy scale at which we expect such effects to become relevant, so the quantum gravity correction to classical gravitation to be effective, is given, as we know, by the Planck mass, which is much larger with respect to the energies that we can currently access in accelerators. And for this reason, our universe represents the most promising resource we have in this field, since the mechanisms of production and propagation of high-energy cosmological messengers could hide some quantum gravity footprints, giving us access to higher energy regimes. In this perspective, an important chance will be offered by the recently proposed technology of multi-satellite telescopes, which are systems of hundreds or possibly even thousands of small satellites in orbit around Earth, all communicating with each other and with the ground itself. So they represent a completely new tool for doing space science directly from space. Multi-satellite telescopes involve very reduced costs, both in the production, because in order to achieve a large number of satellites, a standardization procedure can be applied, and in the launch costs, since they are proportional to the masses of each satellite. And so it will be possible to construct a true constellation of satellites around Earth and to achieve baselines which are much larger with respect to the ones that are allowed by the current generation of telescopes. And this will lead to very high angular resolution when trying to determine the direction of a cosmological or astrophysical source. So let us consider more in detail the Hermes Pathfinder experiment, which is to be launched by the end of 2022. And in particular, it will consist for now in a very small fleet of 6 nanosatellites with these dimensions that are 30 times 10 centimeters, and that will be launched in the low Earth orbit, taking measurements in the KeV-MeV range. In particular, the Hermes experiment will be followed in 2050 by the Grail Quest mission, which will have a fleet of hundreds and thousands or thousands possibly of these satellites, which has as its main goal the one to probe space-time granularity down to the Planck scale. So let's briefly recap how a system composed of different satellites can determine the direction of a very distant source for which we can apply the plane wavefront approximation. So we consider the special relativistic case, and we stick to 2+1 dimensions for the simplicity in the geometrical construction in order to have a clear picture of what happens. In this case, we will need at least 2 satellites to determine this direction. In particular, if alpha is the angle that we want to measure, so the one between the direction between the 2 satellites and the propagation direction of the photons emitted by our source, then how can we measure alpha? By considering the time that the signal takes to propagate from the satellite A to the satellite B. In fact, if we put c equal to 1, this time will be simply given by the distance between the 2 detectors projected along the direction that is orthogonal to the propagation one, so projected with the cosine of alpha. So our satellites, since they are communicating with each other, can measure such delays in the propagation by considering cross correlations between the signals that they receive. So this is, for example, a typical light curve for a GRB as it would be seen from the satellite A and from the satellite B. And obviously, the thing that is very interesting for us is that the precision for the angular measurement increases, roughly speaking, as the square root of the number of satellites. So we see how many orders of magnitude we can gain simply playing with this quantity here. So in the context of quantum gravity phenomenology, such high resolutions could lead to tests of very tiny angular effects, because any quantum gravity effect is expected to be suppressed by the quantum gravity energy scale. So let us consider one of these effects, which is known as dual lensing, and which arises in the context of deformed dispersion relations for frameworks which generalize the relativity principle by considering deformed Lorentz symmetries that are compatible with our dispersion relation. In particular, dual lensing arises from the deformation of the boost sector of the Lorentz group. So again, we consider a 2 + 1 dimensional case, and we consider a source which emits 2 massless particles, so for example, 2 photons, a hard one, so a high energy photon here represented in blue, and a soft one here represented in red, under the same space direction. So we see here the projection of this direction in the x1, x2 plane. What happens in this context is that under a deformed boost, the 2 photons will no longer have the same spatial direction, and in particular, the angle between their propagation direction is proportional to the energy difference between the 2 photons, and if we can neglect the quantum gravity corrections for the soft photon, then it will be simply proportional to the energy of the hard photon adimensionalized by our energy scale. Then, if we consider a reference frame which is not only boosted but also translated in order to receive the soft photon in its spacetime origin, what happens is that since the hard photon is propagating in a slightly different direction, for a point-like observer, it will not even cross its spatial origin. And so we see that this description, that is the one that we find in literature, is not suitable for an analysis that may be performed with multi-satellite telescopes, because each satellite will be point-like, and so it will not receive the 2 photons that are emitted in the same direction. And obviously, we have no way to even understand whether the 2 photons were emitted at the source in the same direction or not. So what we propose is instead to consider a soft photon which is emitted in a direction such that the detector is along its future light cone. So since this is truly special relativistic, we know how to do this. And then we ask ourselves if there is a hard photon emitted in an arbitrary direction to be then determined that will cross the spatial origin of our observer. So will there be an observer, a photon that is received by the same detector that also receives the soft one? And we find that there is such a photon. And what is more interesting is that in the observer reference frame, this photon again comes with a different angle with respect to the soft one. And again, this angle is proportional to the energy of the hard photon. So we have a prediction that we can use for triangulations. So let us again consider the special relativistic picture and then imagine how this will change in the context of dual lensing. So in special relativity, we will only have one wavefront to which all the photons, no matter what their energy is, belong, so they all propagate with the same energy, and we have just one delay in the propagation. But if there is a dual lensing, then what we can expect is that photons of different energies belong to different wavefronts and will have different times to propagate from one satellite to the other. So we know what is delta t here, that is the time needed for the soft part of the signal to go from A to B, and we ask ourselves if in this framework the time that is instead needed for the hard wavefront to propagate from A to B, delta t tilde, is different from delta t, and which is the order of magnitude of this difference. So here is just a preliminary picture of the result that we obtained. So in particular, the corrections to this time delay are exactly the ones that we would expect both from dimensional considerations and from physical considerations. So it's quite a consistent result. In particular, the effect depends on the hard photon energy, and this energy comes adimensionalized with our mass scale. Then we have an amplification that is given by the distance between the two satellites. So let us better understand what this means. Since we are considering angular effects that are, sorry, I don't know what I did. Okay, sorry. So since we are considering angular effects, so which are transverse with respect to the motion, we do not expect the dimensionalizing factor to be given by the distance between the source and the detector, because this is typical for longitudinal effects associated to the propagation. For angular effects, it is reasonable that the effect will be as large as the baseline is. And so we also understand better why we are so interested in multi-satellite analysis. And finally, since we computed these corrections to the time delay by considering considering the finite boosts, because we wanted to understand whether there is an amplifying factor or not, we found a result that is quite encouraging, because we found a dependency that is exponential in the boost rapidity, and so this effect can be actually amplified if the source is highly boosted with respect to us. And so for this reason, if we choose the right source, this effect might be actually visible. What are our future perspectives? Of course, we will need to refine our calculations, and what is more important is to consider different scenarios in which dual lensing is predicted in order to obtain a result that is model independent. Then we will need to consider the physical case, so the 3+1 dimensional case, where we will have two angles to deal with. And finally, we will need to consider other possible measurements that are of physical effects predicted in this framework, and what is their interplay with this prediction of the dual lensing, and so which constraints we can now put from different kind of measurements. So thank you for your attention.
We have time for questions. So.
It's more like a small curiosity, but why there is a dependence exponential with rapidity?
Well, mainly the answer is it depends on which kind of transformations we are considering, but also we expected it because we know that the boost sector is non-compact, so we do not expect like something oscillating, we expect something that is with real exponentials. So it is reasonable, even though obviously it comes out of the finite transformation. So in literature, there are all the calculations performed at the first order. So in this rapidity, and obviously we reproduce these first orders, but we wanted to go to the finite case to understand if this can be an amplifying factor or not.
Okay, thank you.
Yeah, it's quite interesting to notice that Domenico in the previous talk had the exponential dependence of the time delay, the boost parameter, but there was suppression. So time delays get suppressed apparently with boost, while you have this dual lensing get enhanced. It's kind of interesting.
Yeah, the fact is that we get an hyperbolic cosine. So there is both the suppression and the amplifying term, they combine, and then we get a function that is then even in the rapidity. And so both sources that are receiving from us or boosted towards us will have the same amount of angular effects. And yes, that's not intuitive, for example, for me. Maybe this might be model independent, but for now we just checked it in two models. So that's why this is important to consider different models and to understand whether there might be also some suppression. But again, then what will be important is to consider the right source. So for instance, one thing that I wanted to add is that, for example, with respect to time lags, in this case, we do not necessarily need sources that are very instantaneous in time. So these analyses are also suitable for periodic sources. So maybe not only gamma ray bursts, for example.
Yeah, just a question. In this set of satellites, for which I will recognize that the cloning is already a big step in relating it to a meaningful expression. Which are the characteristics concerning the gamma detection? Because those are rather small satellites, and therefore I can assume that the threshold is going to be quite low. So which is the foreseen energy range for these studies?
For the Hermes, the energy band will be, yes, as you say, will be in the soft gamma part RDEX, because KAV, from KAV to MEV. But then there will be a long time before the launch of the Great Quest, and hopefully there will be a technological improvement, because of course it will be interesting to make this analysis considering again high energy messengers. But I'm also not expert on this technical part. But as far as I have read, the idea of Hermes is just to understand whether the feasibility of this project, and then the true technical adjustments, which one are needed for the Great Quest. So hopefully it will be a larger energy band, but of course I'm not even sure it will be feasible. So.
Again, Maria Grazia. Let's take off break now for 20 minutes. So let's meet again at 5:20. And there is still one talk missing. I think it's online. So, all right. Yeah.
Thank you. Monsieur. It's on for me.
Ah, it's online. No, but it's online. Yeah, come like this one.
Yeah, but the slide is online. I think they just share the screen on Zoom.
Yes.
You don't need it.
Yeah, no.